Okay, one more example for this lesson, or for part one. One more example for part one. Use mathematical induction to prove the formula. All right, so that's part one, or that's one example. Let's start a new example. S sub n equals 1 squared, 2 squared, 3 squared, 4 squared, plus n squared equals n times n plus 1 times... Oh, we got to get more room. Wrote it too big. Okay, plus 4 squared plus n squared equals n times n plus 1 times 2n plus 1 all over 6. So again, first step is to prove that the first term is true. So if I plug in a 1 here, I'm going to say, okay, well, my first term is 1 squared. So does that equal, every time I take this formula right here, I'm going to plug in a 1, and I'm going to say 1 plus 1 plus 1 plus 2 times 1 plus 1 all over 6. This is 1 times 2 times 3 over 6, which is 6 over 6, which equals 1. So yes, we proved part 1 to be true because we got 6 over 6, which equals 1. So now the next step is to, when we'll change colors, the next step is to assume that our equation is true. So assume that S sub k is true, which again is this equation that we just talked about. Oh, here, that's not quite correct. n plus 1, 2n plus 1 over 6. And then we will show that, oh, I used n's and k's. Shoot. That's the one thing you have to be consistent with. You have to keep, so again, n's are more like with the series in the original equation, and then k's you use when you are actually solving the mathematical induction. Again, not going to dock you points unless you do what I just did, where you use an n and a k. So you got to be consistent the whole way through. So now we're gonna show that the next term, k plus 1, and every time I see this idea again, all of these first parts are going to be repeated. All this stuff is going to be repeated. The only part that's really going to change is this part at the end, where we have n squared, or, yep, I did it there too, Mr. Larson. Okay. So I'm going to plug in k plus 1 every time I see a k. So k plus 1, and then k plus 1 plus 1, and then 2 times k plus 1 plus 1 all over 6. There we go. And now we can start simplifying. So as I simplify this, I get k plus 1, k plus 2, and 2k plus 3 over 6. So what we do is we go through, we got this, we have our nice formula. We're going to say, all right, s k plus 1 equals s of k plus a k plus 1. So I know that all this first part that we highlighted in yellow up here is going to be the same. So again, if you think about it as 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1. We have the additional one. We have the next additional term. That's what's new, is right here. So I'm going to, again, think about, I already know that this is true right here because we found it to be true. So I'm going to plug in this orange section for my first section here and say k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. K plus 1, 2k plus 1. So I'm just multiplying through. Plus, I'm going to get rid of my my denominator. So yeah, what I did was I multiplied this term by 6 so that I can get it all written in the numerator. So now it's all over the same number, which allows me to now simplify and add like terms in. So equals, and again, this is just a lot of foiling. K times K, K times 1. And then you have to multiply that out. So as we go through, we're going to get, okay, I'm left, K plus 1. Plus 6 k plus 1 squared. All I'm doing again is multiplying this k on the outside into each of my equations. So equals k plus 1. K times 2k is 2k squared plus 7k plus 6. Actually, this one. And then again, it's still divided by 6 here. So as we get down to it, again, what you want to start noticing is that if you're doing it correctly, things are going to start canceling out. Things are going to start combining like terms. You should be seeing things like that's the goal. If we're proving that it works and we know that it works, you need to kind of just self-check and say, hey, am I getting things that are going to combine? Am I getting things that are going to add up? So if I look at my 3 terms right here on top, and we look at what we started with, I think that yes, the next term, and then we still have our denominator as the same. So we can say that yes, it is true, because when we plugged in sk plus 1, we got the same thing as when we got sk. So we proved that it was true. This is a lot of work. There's a lot of places you could goof up or go wrong. Again, you got to write everything out. You got to make sure you're following order of operations and you're only doing one step at a time. If you go through too many